Hello and welcome to this video. In this video, we will study about general trees so that we can progress towards B and B plus tree after looking at multi-way trees. I was sick for quite some time, so I could not make videos, but now I am good in good health. So here is this video for you. So as you know that we have covered binary search tree, red black trees, ABL trees, split trees. So we will now study general trees or multi-way trees. They are also known as M-array trees. That is, they can have M children. These trees are very useful, particularly, for example, in database indexes and so on. And there are many other uses of these trees. They are very efficient for certain kind of operations and are very useful in real world. For example, if you look at multi-way trees, that is B plus trees, they are used in creating index in database, as I said. Similarly, there is another kind of tree which is called log structure merge tree, which is used in a lot of NoSQL databases. For example, CockroachDB makes use of uh, LSM tree. So we will first go through some definitions, not a lot, and then we will see certain declarations, functions, and how a tree is structured. So a tree is finite non-empty set of elements in which one element, and there should be one element is called the root, and the remaining elements are partitioned into m greater than 0 disjoint subsets, each of which is itself a tree. Each element in a tree is called a node of a tree. Each node may be the root of a tree with 0 or more subtrees. A node with no subtrees is a leaf. We use the terms father, son, brother, ancestor, descendant, level, and depth in the same sense as binary trees. Degree of a node in a tree is the number of its sons. An ordered tree is defined as a tree in which the subtrees of each node form an ordered set. The first son of a node in an ordered tree is often called the oldest son of that node, and the last son is called the youngest. A forest is an ordered set of ordered trees. So by ordered, we mean either decreasing or increasing. So for example, a binary search tree is ordered because all the elements in left subtree is less than the root and greater than the root in the right subtree. So that's the kind of order we mean. Every binary tree except for the empty binary tree is indeed a tree. However, not every tree is binary. A tree node may have more than two sons, whereas a binary tree node may not. Even a tree whose nodes have at most two sons is not necessarily a binary tree. This is because an only son in general tree is not designated as being a leaf or a right son. Whereas in a binary tree, every son must be either a left son or a right son. So the way to declare these trees is that I will present three ways. One of the ways is that we put all the sons in an array. And we have a father node, we have the info of the node. The other way is to point to the oldest, point to sons using an array. So in this cases, the restriction is that uh, the declaration forces us to use a constant number of elements for sons. So that is the maximum number of sons you can achieve. There should be a pointer here to next and a pointer to son and father. Anyway, so the third way to present is by using dynamic allocation. So we have father, we have son, we have next. So this father node will point to the father node, son will point to son, and next will point to the next youngest son. Now, for such a dynamically allocated tree, if we look at the structure, it is given here on the right side. The top box represents the next pointer. The middle box contains the info, and the son is contained in the bottom box. So A is the root of tree, A's son is B, B has next sibling C and then D. D does not have any Further, D is the youngest son. It does not have further sibling, and its son is G. B also has a son E, who does not have a son, but it has a sibling F, which is which does not have either of further siblings or children. So how do we traverse such a tree? I have given the code for in-order traversal here. We can implement pre-order and post-order based on this. So we supply the root node. A comes in. A is not null. So we go to sun. Okay. So we go to B. B is not null. So we go to its sun. So we go to E. Now we go to E's sun. So it is null. We come back. So we come back to E and then we print the info. So E will be printed and then we move on to next F. So F does not have any sun. It's null. So its info will be printed and next is also null. So it will come back to E and then it will go back to B. So B will be printed and then it will go to C. C does not have a sun. So C does not have a sun. So C will be printed and then it will move on to D. D has a sun. So it will go to G. G will be printed and then it will come back to D. D will be printed and the stack will traverse back to A and A will be printed. So that's how in-order traversal will work out in this case. Now, one of the common operations is that to assign a list, linked list, a linear linked list as a son. So in this case, we supply the node and the list. Now, if P is null, then of course the node is invalid. We exit. And if it already has a son, then it is invalid to assign to another son. So this should not be P must have a son. It should be P must not have a son. So if P's son is null, we assign the list as son to P. The other operation is to add a son as youngest to the list. So this is like appending to the list, linked list. So the logic is same. We have a variable q. If P is null, then we exit. We take another node pointer R and we assign P's son to Q. Now, while Q is not null, we iterate on the linked list so that R will contain the last element and Q will be eventually null because last node's next will be null. We allocate an element for Q and make its next null. Now, first we consider the case that R is not null. In that case, R will be the last element and last element's next will become Q. So that is an append operation. The other possibility is that P's son is null. In that case, X will become the oldest son or the first son of T. Now, if P's son is null, Q will be null here, and this while loop will be skipped. So R will remain null. Now, if we find here if R is null, then we set P's son to Q. So that's how we add a son to a linked list. So with this, we come to the end of this theory part of general trees. In the next video, we will study the theory of multi-phase trees. And after that, we will implement B and B plus trees. So stay tuned for those videos. And I hope that you have found this video useful. Let me know what you think in comments and how further I can improve on making such videos. And if certain topic invokes interest in you, let me know and I'll try to make videos on those. So thanks a lot for watching. Happy programming.